started sound last time. Is there any question?
Yeah.
What?
About what you wrote on the notes.
Yes. Yes. Okay. That's it.
Yeah.
So in the notes there was a term. And I wrote it like meaning this term, which at the end turned out to be the speed of sound square. It is time independent, right? So that was somebody asked the question. Anyway, so what we assumed, what was our setup? Our setup was a static fluid which is not moving, no velocities before perturbation, and its density was after perturbation, and pressure was like this. Okay, and there is no heat exchange in the system, or the perturbation is adiabatic. So the perturbation is not taking heat from the system, not giving. So in that case, if you are aware, have you come across this equation? For adiabatic system, this is equation of state. You know this, right? P equals to right? So this is general for ideal cases. However, if the system is adiabatic, this is the equation of state, where K is constant of entropy. We start from here. So we take the derivative. Okay, anyway. But we perturb this P. So it is P0 plus P prime, and same density is also perturbed. So what will be the pressure here? Pressure will be okay, I just put the video over there. Now, the assumption here was that rho prime is much smaller than rho 0. Very small perturbation. So I can expand this. Let's take out rho 0 first. Okay. Now this rho prime or rho 0 is much smaller than rho. So I can expand this to Taylor series. And there are second order terms. Second order terms contain rho square over rho 0 square. So we ignore this. So open this. What is this? If P equals K rho to the gamma, P0 is K rho 0 to the gamma. Gamma is adiabatic index. You know, it's Cp by Cv. Ratio of specific heats at constant pressure and constant volume, which is constant. So this is P0. P0 plus this term. Now P is equal to P0 plus this, which means if I take out this P0 this side, P minus P0 equals this term. If P minus P0 is P prime. P prime is rho prime. P prime over rho prime equals what is P prime? P prime is P minus P0, change in pressure, P prime. What is rho prime? So rho minus rho 0. Just put it here. Adiabatic equation of state, so everything is at constant entropy. Okay? So this is automatically assumed. So this term is time independent.
What does this index mean?
Index means entropy is constant. Sorry, constant. It simply means entropy is not changing. Entropy is not changing means system is not taking any heat from outside or the input. So this is time independent term. It's rho 0. It's equilibrium density. Everything else is constant. This is why we assume that this does not depend on time. And this is how I took it out. Okay. However, this is not always true. If you assume second order terms, they will be there. So assumption is that when you take the partial of pressure with density, first order, within first order assumption, you can take out from the time dependent. Okay?
Alright, thank you.
Alright. Last time I just said that because it is derivative, so it's just basically ratio of the perturbations. So ratio of two perturbations is what it assumes is that, okay, what it physically means. It physically means that the change in pressure because of the perturbation and change of density because of the perturbation, they are basically it's identical changes in magnitudes. This is why the ratio does not change with time. You asked this question, right? Yeah, I think you asked the question. How did this come out of the time derivative in last class?
I don't remember.
Okay. Anyway, this is the answer. We take the equation of state of adiabatic systems, just expand it with Taylor expansion, and then we show that if you ignore the second order term, this derivative simply turns out to be time independent. So you can see it again on YouTube later on. Very straightforward anyway. Okay, so we start today's lecture. Anything else? So what we did last time, we derived the wave equation for sound, and we showed that within several assumptions, the perturbation caused in a fluid propagates with certain speed, sound with the speed this, which is sound speed square. Now, when this turns out, when this comes out of the derivative, what we assume this is time independent. What we say that the speed of sound is also time independent. Okay, that's also an assumption within first order. Okay. Now sound is a wave, and waves have energy, like particles. Throw a stone, stone has energy. Sound is coming, that also has energy. If somebody asks you, how do you know the sound should have energy? How do you know practically that the sound waves carry energy?
Well, it's motion of particles, so
Motion of particle, okay, if I am speaking from here, the motion of particles is like this. But what particles are not coming to you?
the
Particles are just oscillating here, the disturbance is propagating. What is propagating in the disturbance? We say propagating. When you put the small stone on the water surface, you see something is going out. But practically nothing is going out, nothing is seemingly going out. It's just a particle oscillating like that.
But you can see waves gaining height, the speed.
Gaining height.
Yeah. I mean,
What do you mean gaining height? Height generally decreases because the wave goes like this. It decays. Typically, in a dissipative system, with distance, wave decays and is also expanding radially. So it does not gain height.
I mean, the molecules on the surface, if I throw a stone, then some of the molecules will go up. Then
Molecules are going up, molecules are coming down. They are doing like this. But the water molecules are not going anywhere.
No, it's density of the air.
Density of air. So the density changes. When I'm speaking, small region becomes denser, then becomes rarer. So particles are oscillating like this. And then other particles are also oscillating like this.
it's pressure, right?
Pressure? What?
No, I mean, I asked if it creates a
What was
pressure.
the pressure?
It does create.
So
It does create pressure change as well.
There is a force,
There is a force. So
energy.
the energy propagates. So when one oscillation takes place, another oscillation takes place, one oscillation gives energy to the other part. This is how it propagates. But my question was different. How do you know that, hey, okay, now you physically visualize this, the process and you said that you are applying force, the energy should propagate. But how do you know from your experience that sound carries energy in momentum? If some child asks you, 7, 8 years old child, you will not tell him force and pressure, right?
You can
Do you experience?
like opera singers that breaks glasses.
Plexiglass.
Yeah, and
That's it. Okay.
how does it go?
In right frequency.
You don't need to go to opera singers. You can simply see that when the weddings parties take place, the sound system is there. You see when there is a sound, everything is vibrating. Right? How do you listen? Sound waves come and they collide with the eardrum. Eardrum vibrates. Now, if something, when I'm not speaking and not listening to anything, your eardrum is static. When sound waves come, it starts vibrating. It's mechanical vibration. So initially the motion goes zero, then it starts vibrating. So when something starts moving, it has momentum. Where it has come from sound waves. And it also oscillator has an energy. So this is how sound impacts. So it carries energy. Every wave carries energy, so the sound waves. Now we'll calculate what constitutes of that energy. Okay? Mathematically. Yes. What? I said a lot of things. Sound carries energy.
Okay.
You are listening to me.
Yes.
How are you listening to me? When sound waves come and fall inside the eardrums, there is a eardrum inside. So when the sound waves come and falls on that, it starts vibrating.
Yes.
It vibrates only when energy is transferred to this. If you do not give it energy, it will not vibrate. In fact, oscillator has an energy. So this means sound waves carry energy from my mouth to your ears.
Okay.
This is what I said. It's very simple. Okay? Now we quantify. Energy density of sound. What is the energy density of the fluid? We have dealt with it a lot. Let's say energy density of the fluid. Okay, let's call it fluid. Let's go easy. Let's call it E. It's if a fluid is moving with velocity v, this is the total energy density contained inside the fluid. If it's not moving, you only this part. What is this? Density multiplied by
Specific. No.
internal energy density. Internal energy. Okay. What is contained inside the particle's motion, basically. Like You should have physical picture in mind for everything that you write. When you give heat to a system, like you heat up a pan filled with water, the heat goes in two parts. It increases its internal energy and it does work. Two components.
Is Q.
Q is heat.
Ah.
This is first law of thermodynamics.
Yeah.
We have used it a lot. And you might be using it in thermodynamics class as well. It increases the internal energy density, which is this. Okay? It also does work. Work means if you boil milk, what happens? Expands. Expands means volume increases. This is the work. Okay. So this is internal energy of the fluid. Now suppose the fluid is not moving, our fluid is static, it's not moving at all. So V is 0 for the fluid. But we know that when you perturb the system, what you do? You induce some velocities in the fluid itself. The density oscillates here, particles oscillate. So now here V is oscillation because of the perturbation. Alright? Yes. And we use the same equations. Energy was also like that. Okay. Now I can replace this rho and epsilon from the slightly perturbed values. And we deal with these two terms in different manner. First term is rho e. Let's expand it around density. Because this change in rho and e, this is a second order term. Rho is also perturbed, e is also perturbed. There are small perturbations in both. So we can expand it around density of the fluid. So call it rho 0. This is initial one. This is our first term. I just expanded it around density. Now, in the previous answer I said that we ignore the second order terms. Here I have taken the second order term. And the expression will be given shortly.
Why do you think?
The answer will come. Whenever we took second order terms, even in previously in a couple of examples of viscous fluids, when the first order term turns out to be 0, then your second order effects are important. Why do you ignore this? Because this is much smaller than this. However, in specific cases, when the first order term goes to 0, second order term becomes important. But we will see it shortly. And the second term is, this is first term. Okay? And the second term is which is okay. Now this term is 0. 0 means much smaller because this velocity, what is this velocity?
The oscillation. The oscillation.
Of the perturbation's velocity. So it's very small. This perturbation is also very small. So we ignore this term. This is rho 0. So in second term we are left with only one term.
You can ignore this term only by mentioning that that rho is very small.
No.
Because the other term has a v squared as well.
Right, okay. So this is basically third order term, the way we say it. This is second order term, v square. If we ignore second order terms everywhere, this is also 0. But, so this is second order term, this is third order term. So v square is same in both, you are right. But we ignore this because it is one order higher than what you are taking here, second. Okay, third order term. This is O3. Alright. Now we have to solve this. So when you give heat to a system, this is first law of thermodynamics. Heat goes in two parts. However, if the system is adiabatic and perturbation is adiabatic, this is 0. So dE is minus P0. V is specific volumes 1 over density. So this becomes minus P plus P over rho square d. Okay? For adiabatic systems. Right. If I take del E over del rho here, you need this here. Everything is at constant entropy, okay? So Joule. So del E over del rho equals P over rho square. Okay. I'm not dealing with this term at the moment. We'll talk about it later. So rho 0 is 0 plus rho prime rho. So cancels. So this is simply E plus P by rho. What is E plus P by rho?
Specific.
W, specific heat, specific enthalpy. So this is only W. So I write it like this. Okay. Now we deal with another term, third term. Because the first derivative was W, second derivative is simply okay. dW dO. So let's write it like this. Constant entropy what is this? What is this? This is sound speed square, C square. C square Now I have to find this dW over dV. What is W? Okay. Now we know the D is this. We use this expression again. From here, I find okay. I put this here. First one, so it becomes D. These terms are equal, you can see. So finally you have 1 over 1. dWdP is 1 over 1. This is C square over 1. Okay. Plus okay. Next. This term is line square. Right? And then we add this term, second term, which is only this part. So final expression of E is I took only the first term here. Okay. So this is the energy density contained inside the sound wave. If you calculate the total energy, just integrate it over the volume. Let's call it total energy. Integration of E in your entire volume. Okay. So ET becomes integration over entire volume. Let's call V0 because V already we have for velocities.
Wait, but without the integration, what? Which kind of energy?
Energy density.
Oh, okay.
Energy density is important.
Okay.
Energy density is only which is important thing, but we have to look into this. This is not the energy density of the wave. This is the energy density of the fluid. Okay, we are still dealing with fluid, but we have to take care of what is the energy density of the wave only. So like the first term, rho 0 is 0. It has nothing to do with wave. Okay, this is intrinsic to the fluid. So even if there is no perturbation, this term is there. So we have to see which terms contribute to the energy density of the wave only, sound waves. So you see, when you integrate it over the volume, and you note that the first term does not contribute to the wave because it is intrinsic to the fluid. So it is not important. Okay, it is not 0. It is the biggest term, but it is not the energy density of the wave. We are still dealing with the fluid as a whole, along with the perturbation. If you look at the second term, rho prime, when you integrate, what it gives, what is the integration of rho prime over dV? What is rho prime dV? It's mass. So the density perturbation is given, but does that perturbation add any mass? It doesn't. Total mass is mass. If I speak, I am not adding more mass to the fluid. So this term does not contribute anything because the mass is not added. It's still constant. Total mass is constant, no matter how large perturbation we give. There will be no linear perturbations with the energy increases, but that's a relativistic limit. We don't need to worry about that. Perturbation is small. It does not add any mass. So the first term and second term are not important, or they do not. The first term is not associated with the wave. The second term is not contributing because there is no mass added. Yes.
The integration is over the volume. Like V0 is the volume and the V is the velocity.
Yes. V0 is the volume of. If I am speaking here, the volume of the whole air in this room. Okay. So in this room, no new mass is added, so second term does not contribute to the second term is technically 0. First term is no, total mass is constant, not 0. Total mass is anyway constant. But the first term is of the fluid itself, second term does not contribute in mass, so we don't have two terms in the wave. So we are left with only these two terms. Okay. Now we again write the expression for E. Just taking these two terms. Half this is the energy density of the sound wave. Okay. So when I speak, this much energy falls on your eardrums, given all the assumptions are true. Now how do you understand this expression? What do you see in the expression? We derive, that's fine, but you have to understand it. It has two terms. Which are the terms? You can see it and you should be interpreting
The first
it.
one is kinetic.
First one is kinetic. Kinetic of what? Kinetic of the oscillation.
Yeah.
So if I take a small volume, let's say infinitesimally small volume, and I want to see unit volume, let's say, unit volume, 1 cm square or something. How much energy inside? Inside you have two things. One, something is oscillating. So that something is moving. So that's energy of the because of the motion. And this one, what is that? You should be able to interpret it. It's not difficult. What is the other energy? Just look at the small volume in the air where the perturbation is given, it's oscillating, and that's it. All energy should be of oscillation. What is the second term? What potential? There is no potential.
Not sure.
There is. In oscillation, there is always a potential because it's like an oscillator. But it's okay, it's kind of that, but it's not exactly how to interpret this. Okay, so you look at this expression. Internal energy density of a normal fluid. Suppose there is no perturbation, general fluids. It has two terms. One is kinetic energy, second one is internal energy. So this is the internal energy of the perturbation. Another way of looking at it is from this first law of thermodynamics. It is always there. When you give energy to a system, it does two things. Increases internal energy and does work. So basically, this is the work done by the pressure. When you heat the milk, it expands. Expansion is like work done. So when I'm speaking, there's a work done on the fluid itself. Along with the motion, you can interpret it like a potential energy of the oscillator. That's not a wrong interpretation. But from fluid terms, it is the work which is done by the induced energy of the perturbation. Okay. You can see it right away from here. This is identical. First term. Second term is like this. So if I want to interpret it like rho prime, so this is similar. This epsilon in normal fluid is like this. So this is the internal energy of the oscillator, the system itself. Okay. Now, energy is conserved. Like matter is conserved, we have seen over and over again. Energy is also conserved, momentum is conserved. And when I speak, your eardrum starts oscillating, that means it starts moving. Motion contains momentum. So that means sound waves not only carry energy, also carry momentum. They impart both energy and momentum to the system. Or both propagate. And the energy density should be conserved. What it means? It means if you take a volume, like a volume, small volume, there is some perturbation here, or maybe it's outside, but we take an arbitrary volume, and energy is propagating through sound. So energy is actually going out. So whatever the energy goes out, it is equal to the energy lost from inside, right? Because energy is conserved. So this brings us to energy flux. This is continuity equation. When it is density, it is d rho dt, and this is flux, matter flux. Now it is energy flux. EF is energy flux. Simply states if a volume, some energy is coming out of the volume because of the perturbation, same energy flux, same energy is lost from the volume itself. So this defines the continuity of energy in the sound waves. So we have to find what is this energy flux, how much flux is there, because energy is flowing. Now what it shows is how much energy is there in unit volume. We have to see how much energy is flowing because of the perturbation, which is transferring the energy and momentum to the nearby particles. This is what we derived. It's flux of energy for a fluid. I think in second lecture was energy flux. So this is the flux density of a fluid, but we have to keep in mind that here V now is not the velocity of the fluid. Our fluid is static. V is the velocity of the perturbation. Now we derive the expression for this E. Next is we are finding out how this propagates. Let's open this. This is a third order term now, because perturbation velocity is very small, so it's a cube of the velocities, so we ignore this. Okay? What you have is, this is the energy flux. So it becomes which terms will be neglected here? This is anyway small, which is being multiplied with every term. And this term is 0 because it's second order, it's basically third order. Prime quantities. So we ignore this term. Okay. So now we have three terms here. First term is of the intrinsic fluid. Second and third terms are due to the perturbation. Now again, when you integrate it totally, what you find is there's a rho prime term here. Its meaning is the same. It's mass term. Rho prime is how much mass is being added. Because the perturbations do not add any mass, no mass actually propagates. So we need to draw volume here. Perturbation causes energy and momentum to flow out of the volume, but no mass flows out. It's oscillating, nothing is going out. So no mass is being added, we note it here. So we are left with only two terms. In the same previous argument, we ignore this term as well. If mass flows out, we have to take care of this term, which is the scope of non-linear sound waves. Perturbation is so strong that it is blowing the matter out. Like when you said the glass is broken. That is extreme. That means the sound is so extreme that it is causing dynamics to change. In our linear regime, where we assume that the perturbations are very small, let's say 2 terms. Try to find this. Let's try it again. We found from previous, yes.
Going back again, why did you neglect the third term? Rho prime omega 0.
Okay. So if you take this term, rho prime omega 0, okay, and integrate it over the surface of the volume. Okay. Now rho, what is rho prime? It is the density perturbation. When you integrate the density with volume, you take mass. So this is what it means. What it means is the density flowing out of the system. If the density is flowing out of the surface, then this term is not zero. So basically no mass is flowing out. It's oscillating. The density waves are just oscillating here. Energy is carrying away. But when you take an arbitrary surface, matter is not going out, matter is not coming in. So no mass flux is, this is mass flux. No mass flux is involved. This is why this term is zero. Okay. We saw that these 2 terms are same, remember? From last derivation. You want me to derive it again? Which is 0. If you put this here, you see that these 2 terms are same. So it is simply dW is dP by rho. What is dW? dW is just W prime. Okay? It's the change in specific enthalpy. So this is W prime, P prime over rho. So P prime equals what W prime. So this is okay. Again, the first term is the density of the fluid. this does not contribute to the energy carried away. Same as this term. This is the same thing. Same argument from our previous explanation that no mass actually flows out because of the fluid density, because of the perturbed density. Okay. From the surface, it does not take out mass. What is flowing? Only energy, and only energy is flowing. Basically, that is momentum. So this term does not contribute. So when you talk about the sound waves, we are left with only one term, which is P prime.
Can you explain again the role of each term before?
So this expression, whole expression is this one.
You said one contributes when the energy flows out, and one.
Okay. This you understood, right?
Yeah.
Okay. There are four terms here. When you take this term along with V, it means because of the density of the fluid itself, and when you put the perturbation, this expression is correct. No any term is negligible. Okay? In the expression, this is the biggest term, so it cannot be neglected. But what we are interested in, what is the flowing because of the perturbation? Because of the perturbation, when you take this rho prime, rho 0, and velocity, this mass is not flowing out. Our assumption is that the matter is only oscillating. It's not flowing out of the surface that we assume here. When it does not flow out of the surface, it does not contribute to the energy flux because of the perturbation. This is why we don't consider this. When we take rho prime, what it means is because of the prime density, the perturbed density, is any mass flowing out? No. So this also does not contribute to that. So we remove these two terms. That does not mean the term is zero. What it means is we started with total energy flux of the fluid. Now we are taking into account what terms contribute to the wave's energy density. Wave's energy flux. Basically nothing is flowing out from here. This is why we are left with only these two terms, which include the perturbation of the specific enthalpy. Okay? Yeah. Just one term. So what it means is when you apply pressure, pressure is also energy density kind of. So this shows what energy density is imposed by the perturbation, and its motion is characterized by velocity, how it is flowing out, velocity of the perturbation. So what it means is, suppose there are two oscillators. Initially, this oscillator is not moving. Now this oscillator I just perturb a little bit. Put a pressure on that. Because of the pressure and its velocity v, it is imparting some energy to the next oscillator, start oscillating. Suppose there is a surface here. So matter did not go out of the surface, so all the terms did not contribute. But because of the pressure, energy was transferred. And then this transferred to the next oscillator. And this is shown by the last term. Okay? Okay. So this P prime V, as in the notes I have written it as Q. Okay. Instead of EF I have written it as Q, so not to be confused with that. It is sound energy flux density vector. This velocity is vector. It is simply the perturbation in pressure and the velocity of the oscillator. So what it depends upon? How much energy will propagate? It depends on two things. One, how big is the initial oscillator? How intense is the oscillation in the first oscillator? And how much pressure is being put? That's it. Like my voice is down, so I'm putting less pressure. If somebody speaks loudly, it will put more pressure, more energy will flow. Okay. Now, this is a general expression for any traveling wave. So what if the wave is traveling in one dimension? 1D. It's moving only in x-axis. Then the pressure P prime is given by traveling plane wave moving in only x direction. This I will leave for you in the assignment, and I will show you how to solve it. So what you will do, and I will write in the assignment specifically. You take the Euler equation, perturbation, simple exercise. Perturb the Euler equation, V prime, what we did in last lecture. Take the densities, continuity equations, and perturb it. And then assume the solution of V in form of sinusoidal waves. This is what you derived last time. Put this in both and use the expression of sound speed. Once you solve all three, you will get this expression. Okay? I'll write in the assignment the steps. It's very straightforward. So this is what and it's not in books, so this is why I'm giving. By the way, do you read books?
Time. Yeah, time.
She reads. See, I'm not a professor, so if you are relying only on my notes, it's a very bad idea. Okay? Notes are just for helping. Somebody messaged me that I did not upload the last lecture. The lecture notes are just for assistance. They cannot be the primary source of subject. Okay? My level of explaining is also limited. So you have to go to the books. A lot of explanation is given. I learn from there. You should also learn from there. Take the notes, the help of the notes as well. I may not even, I will give notes for every lecture, but if I don't give it, it should not matter. Discuss things here, and you should always follow books. Otherwise, you will not learn the subject if you don't open the books. Okay? So you shouldn't rely on notes. If I don't upload, I will upload every lecture, but it's just for little bit extra help. If you learn from my notes, that means your whole source of knowledge is my knowledge, which is very bad idea. Okay? It's very serious commitment. You bought the book. Have you ever opened the book of Linda Lipsch?
Yeah, but
It should be available online as well.
which one? Or all of them? You mean a specific book or?
I suggested books in the syllabus.
Digital.
I suggested 3 books. Linda Lipsch is the fundamental book that I'm following. You should always have the book with you. There's not more than what I speak here. We can discuss a lot of things. So you should always follow the books. You cannot rely only on notes. Okay. So if you take P from there, which you will solve in the assignment, Q becomes P prime from there, C rho 0 3. Okay. So this is the flux of the energy for a plane wave traveling in one dimension for that, and this is general expression. And it's fairly simple. Just the perturbation in pressure and the velocity of the oscillator. Basically both are connected. More pressure you put on the fluid, more will be the induced velocity. Okay. So this is one question of assignment. Other than that, you have seen that when we derived the sound equation of sound, wave equation of sound, we had many assumptions. One of them was, 2 of them were, the medium is not moving. It's a static medium, which we always follow. And second, there is no pressure gradient in the system itself. Right? I'm thinking to give a problem in the assignment where you take, if I speak here, let's say, on the surface of Earth, does it follow all the assumptions that we assume? Which it breaks. We assume many things here. When we derive the sound equation, wave equation of the sound, we had many assumptions including the medium is not moving, V is 0. This is the perturbation's velocity. The fluid's velocity is 0. We also assume there is no pressure gradient. So if I look at the air in the earth, on the surface of the earth, and if we speak, which assumption is broken, or does it follow all the assumptions? It's not moving, that we assume two things. The fluid is not moving. Second, it does not have pressure gradient. So we can assume that air is, suppose it's not moving, it's static. But there is a gradient in pressure. Pressure decreases with heights. So I'm thinking to give one, which will be complicated problem of the assignment, putting the general condition like it is a velocity and it is a pressure gradient, how the solution of phi comes out to be. And I'll keep it as an optional question. Somebody can ignore it. Other 2-3 problems that I will give, that will be part of the assignment. Enthusiastic people can solve. And I can tell you that you will not get wave equation. The one we got, beautiful wave equation. Double derivative of time, double derivative of space. It will not turn out to be wave equation. It will be horribly complicated. Then you can solve it numerically using, do you use, which language you use? Do you do computation?
MATLAB, Python.
Python, MATLAB. MATLAB will be better. Python will be complicated. But for the
You can use NumPy.
Hmm?
You can use the NumPy library. So similar.
You can use NumPy, but it can be vectors, divergence, it
Yeah.
takes automatically.
Yeah, yeah.
It takes
It
divergence.
works like
Yeah.
MATLAB.
MATLAB is okay. Okay, then you can use it from there as well. So we'll see how it comes. And you will see it's not a wave equation, but in our experience we always follow. The wave velocity that you find is 300 meters per second. It is observed, found to be true, so more or less it works. Why it works? Because first, we can ignore the air is moving. Second, the change in density at the surface up to few meters is negligible. But when you speak from one mountain, listen to another mountain, I think there will be a problem. We will see in the second. Okay. Now momentum. So now we saw the energy flows. When energy flows, it imparts momentum. The momentum density is, you know this is momentum density. You know it from continuity equation, right? This is J. Put rho. Again, here V is not the velocity of the fluid, it is velocity of the perturbation. Okay. So there is one more question in the assignment, which is if you solve the Euler's equation for simple assumptions, adiabatic systems, you get the solution for J as This is for it's del cross V equals 0. So, given these two conditions, you put in the
What is 2?
irrotational. This is conservative. Perturbations are conservative. We always assume this. And again, the many assumption, this is also a crude assumption. When we assume that the perturbation we are importing, they are irrotational. They remain irrotational over time, but in the beginning, you have to assume that they are irrotational. So if I give the perturbation that does not have any curl in them, the system cannot generate a curl. This can be found from Euler's equation. With the gradient of P, you take curl of gradient of P, which is 0, right hand side. We saw it last time. But it has an assumption that in the beginning, you come with the assumption that the perturbation does not have a curl. So many assumptions. So if you assume these two and solve Euler equation, you get this. I'll give it in the assignment and we'll give some hints how to solve it. Okay?
It seems that the unit is.
Hmm?
It seems that there's some. Like J V is not is the gradient of phi. So
Yes.
it's like the J is a vector and the right hand side, the first term is.
Yes. This is vector.
What about the first one? It's a scalar. Phi
Yeah.
is.
It's a scalar.
So how?
No, it's not square.
Lecture notes, you wrote, yeah.
It's just grade phi. I wrote it wrong. Now it's okay. It's vector. Okay, so this will be in the assignment. Yes.
Is this the same J as rho V?
Yes, it is J.
Oh.
J. So we integrate this J over volume. Yeah, C is sound speed, okay, not light speed. Volume is V0 and not V. This can be converted into surface integral. What is the surface? The surface of the volume element. What it says is that what is phi? It is velocity potential of which velocity? Of the perturbation. If you take a surface, phi is velocity potential. Outside this is 0. If there is a wave packet, there is oscillation in the wave within a certain region. Outside this, there is no velocity potential because there is no velocity. So phi goes to 0 far away. So when you bound the surface, all sides, this integral totally turn out to be 0. Because the potential, velocity potential is 0 outside the surface. At the surface, this turns out to be 0. Which means the first term does not contribute. So we are left with only the second term. The wave's moment. In other words, the first term does not contribute to the wave's moment. So when you integrate this, is this 0? This q over c squared is constant anyway. Sound speed is constant. Q is, where we wrote q. It was p prime v, but okay. Q is simply p prime v. P prime is pressure. So this is the only thing which travels outside the surface, spreads. So because this is non-zero, this is strictly non-zero, it shows that the sound waves impart momentum. They propagate in space. Okay. And why did we consider the second order term? Because the momentum in itself is second order. V is small, V prime is small. First order term does not contribute. This is why you have to take the second. Okay. So now we are done with sound, what I targeted. If there are questions, I will take. Otherwise, we will move to turbulence. Is everything clear? We take a small break. Yes.
Why I get the first term is 0?
First term? This one?
Yeah.
It is 0 because this velocity potential is the velocity of the perturbation. Okay. If you take a bound surface, outside it, the potential is 0. What we are calculating? We are calculating if the momentum is flowing out. The flight does not flow out. It's only oscillating inside. Only thing that goes out is the energy transferred because of the pressure from one oscillator to another. So suppose there is one oscillator here, oscillating. There's one oscillator here, oscillating. It communicates with this. It transfers this momentum. But because it is only oscillating, so velocity does not go out. If the particles go out, then it's a different thing. So the velocity contribution is not there in the wave. This is not the contribution in the wave. So only the contribution is because of the pressure on another oscillator, it is transferring momentum. That oscillator is taking the momentum and is transferring another. So this is what is propagating. This is why I said the oscillators just oscillate, something keeps on propagating. That is this moment. Okay? Let's revise the whole course. What we have studied. We studied inviscid flows. They satisfy Euler's equation. Inviscid.
Okay.
No viscosity. Then we studied viscous flows. What is the corresponding Euler equation for them?
What's the question?
Inviscid flows satisfy Euler's equation. Viscous flows satisfy Navier-Stokes. Okay. Inviscid flows were flows without viscosity, no dissipation involved. In viscous flows, viscosity appears. Which means in certain conditions the flow loses energy itself because of the viscosity. The example was if the water is flowing on the surface, because of the viscosity it is slowed down. Yes, yes. So Navier-Stokes equation should work in principle. What we expect in nature is if viscosity keeps on increasing or velocity keeps on increasing of the flows, these should always work. However, that is not the case. There's a limit where everything breaks. None of these equations work. That limit is for turbulent flows. What exactly happens in turbulent flows? You know what is turbulent. You have seen rivers in two states. When the river is flowing very slowly, it's a smooth flow where the equation satisfies its motion. Then you see when it is very fast, you see something completely chaotic. What exactly changes?
The return of the velocity can change in time. The current velocity can change in time, so
Curl velocity? Curl. What is different? From here to here, what was different? These flows don't have viscosity. Here they had viscosity. Some dissipation was there. This is another kind of dissipation. What exactly changes? We have already started working a little bit towards this direction. This is why I took sound first. In sound, we saw that if you give small perturbation to the system, the picture should be very clear. What is inside the system, what's going on. You take a fluid, you perturb a little bit. Every fluid has many perturbations automatically inbuilt in the nature. Okay? Perturbations are always there. But when the flow satisfies Euler equations or Navier-Stokes equations, what it means is, if you give it a perturbation, the system is so strong.
No, we just said that a minute ago. Yeah.
The system has ability to eat up the perturbation. Like the sound. Give small perturbation, what happens? The system remains stable. The sound does not destroy the system, unless the example that you gave, the glasses are broken in opera. That's the non-linear regime. Turbulence is a non-linear regime. So when you give a small perturbation, there are two types of perturbation. One, you give a perturbation, the perturbation decays with time. Same our favorite example, you put a small pebble on the water surface, the waves are generated. Those waves decay with time and the water becomes still again. The second types of perturbations, when you perturb the system, something happens, the perturbations start growing.
Chaotic systems.
Yes, but how will the perturbations grow? It takes energy, grows.
Okay. Maybe the medium itself is has turbulence.
When you say perturbation is growing, what does it mean? We studied now that the perturbations have energy.
Energy enters into the system.
Energy enters into the perturbation.
Yeah.
Okay? The perturbation takes the system's energy and grows it down. See the example on the beach. When the sea is pretty quiet, then there are small waves. When there are small waves, that means They're dying. Small waves, they're completely decaying. But after some time, you see that something is happening. The waves are just adding together, and it is becoming monster waves. So the system is turbulent. Then they say, don't go into the water. Then we have to come back because it is turbulent. So it's the game of how the perturbations behave. I gave you a very crude example last time. If you slap an animal eats up the perturbation. It doesn't even move. Calm. If you pinch, if you prick it with a pin, same perturbation, it's very small, but it grows. The perturbation takes the energy of the animal and then it starts running. Basically the same thing happens. But the question is, why would a perturbation grow in fluids? It grows in animals because they sense that something dangerous is coming, it can break over the structure. So it's a biological system. But why would the perturbation grow in fluids?
Maybe the system is an unstable point. It's like you have what is called a quality point, and it can be stable or unstable.
System should be unstable point. Yeah, this is unstable.
Yeah.
This is stable, but if it is pointed, it is
Pointed.
unstable. Then small perturbation, ideally it should stay like that. Small perturbation will make it fall down. But this does not look here. System is flowing, its velocity is increasing. I don't see any instability there.
Why? The steady state can be an unstable equilibrium.
Steady state unstable does not mean system is unstable. See? Steady state unstable means the system's properties are changing with time. Speeding up, slowing down. And my favorite example of turbulence is the stream from tap, small stream. There is no pipe, nothing. It's just the stream which is falling inside. In the beginning, you see it's very smooth, and then at some point, it becomes turbulent. That means whatever the perturbations were there in the beginning, the system was responding to the perturbations in such a manner that the perturbations were decaying in time. But after, when gravity velocity increases, speeds up. After a certain distance, speed increased, the Reynolds number changed, increased, so that it became the perturbations after they kept on going. At the last part of the stream, whatever you see is a non-linear perturbed system. So why would the system behave like this? It is not fully known. The perturbation, the turbulent flow is something that we still don't fully understand, how the perturbations grow. But we know for sure from mathematics and physics that whatever is happening, it is perturbations are somehow growing. We know a little bit, but we don't know much. We only do the experiments. So in experiments, so in the tap water, when the water is flowing down, ideally it should always remain stable. The perturbation should always decay. See, because perturbations are small. They are not large. So they should decay, but it doesn't decay. After a certain level, it becomes turbulent. So it is not well known, but there are other cases where we can well understand how the fluid becomes unstable. So mainly we will be dealing with instabilities in fluids. I think in syllabus I have written 4 instabilities. Taylor, gravity waves, the one waves on the surface of the water. Kelvin Helmholtz, I think 3. So we study 3 instabilities. Instabilities are also the same thing. Where we understand, if there is unstable system, small perturbation breaks it. Give me example of unstable systems. Fluids.
Ocean.
Ocean is
It's unstable because it's always.
ocean is all huge. There are many things. Everything is happening with ocean. Let's be specific. Have you seen an unstable fluid?
Maybe like flow around the wing that goes like flutters away behind the wing.
Flow around the wind.
Wing. A
Wing.
wing of an airplane. You see behind it, it goes like it flutters. It goes
You
to
mean
the
the flag?
like a stall or something.
Storm. What storm?
When a plane stalls when there's not enough air and the air behind it just goes.
Ah, turbulence. You mean the turbulence during the flight?
I guess.
Turbulence we already talked about. But other than turbulence is something that is there's a lot to discover yet. Physics is not, even classical physics is not complete yet. But I'm talking about simple, unstable fluids that you are familiar with. Let's take a simple example. You have water.
Hot fluids maybe?
Hmm?
Hot fluids?
Hot fluids.
Yeah.
Why hot fluid will become unstable? You see the smoke coming out of your milk when you're boiling it. That's hot air, right? Not necessarily it is turbulent or it's unstable. It's not unstable. It's moving up, but it is not unstable. So let's take a simple example. You take water and kerosene. Kerosene's spelling, I don't know. You know kerosene? So let's, kerosene is like petrol.
Like what?
It's less density having fluid. We can call it petrol. Let's call it petrol. Because I know petrol spelling, so let's call it petrol. It's PRPE.
Can you draw it maybe?
What draw? What do you put in your bike? Fuel. Petrol.
Gasoline.
Petrol.
Okay.
I think it is PATROL. Okay, I'm familiar with kerosene that we used to use in our homes for cooking. That is also kind of
Diesel,
it is-
benzene, we have like tons of names for it.
Hmm?
We have tons of names for it. Where it's loaded.
Okay, but you understood what I mean.
Yes.
So the kerosene is less dense. So when you put it on water, it does not go inside. What will happen if you put petrol on water? It floats. Its density is less. It's less denser. This is less denser. This is denser. So if you take anything, and put water at the bottom, petrol here, what will happen? System will remain stable. What if you make it upside down? Now what?
It wants to flip.
It wants to flip. What will happen?
It can't do it smoothly because
If it was uniform, then it
Just
will
fast
stay
food.
like that. But small changes, small fluctuations in the perturbations in the area.
Perturbations
it
are
may-
always there. Yes.
Yeah.
So in the interface, small perturbations because of that,
That will make the
this will come down.
yeah.
Okay. So this is instability between two interface of two fluids. Okay. All the instabilities are like interface of two fluids. So this instability we will study possibly in next class called relative instability. This is we understand. This is you physically understand as well. Small perturbation, it will make the system unstable. What are the other examples? Where there are two fluids. These are the cases where we understand the instabilities.
like what example?
Similar to this, what examples you see in the atmosphere or surroundings?
When you have a water bottle and you open it and drain it, it's like it wants to come out, but air wants to come in, so to
Yeah.
find this weird like sort of chaotic
It's an
balance.
example.
Same thing, yeah, right.
Yeah.
But the air's density is so less that it is basically behaves like it is falling in vacuum.
Yeah,
It is still instability, but okay.
and yet the vacuum forming at the back of the water
If the
bottle will
bottleneck
force
is
it to fill it
very
with air.
tight, then you see it like
Air
that.
will be forced in.
Ha. So you see the bubbles go inside.
Yes.
Basically, there's the same instability we used to. Another example is Kelvin-Helmholtz instability. You see the clouds. In the clouds, you see a peculiar structure like this. I'm very bad in drawing like that. these kinds of structures you see. Go to your home and type Kelvin-Helmholtz instability in clouds. You will see. The clouds have this peculiar structure. Why this structure is formed?
Surface tension.
Surface tension.
I don't know. Why would it form?
Can you repeat the question?
In the clouds, you see turbulent kind of structures, like they are locking with air. I will add a few pictures maybe in the notes as well. That happens because there are two fluids. One is the cloud and air. So there is a relative motion between these two. When there is a friction between two fluids, the interface becomes unstable. And this is known as Kelvin-Helmholtz instability. Not always. If one fluid moves on another fluid very smoothly, it's not unstable. There's a limit after which both become unstable and you see these types of instabilities.
But don't you have a sort of sticking condition when you have a boundary? On a boundary for viscous flow that isn't turbulent, isn't it supposed to be that like there's no the velocity is equal at the boundary, it can't rub against each other?
Velocity is equal, there is no instability.
But you say that if you move smoothly across the fluid, as if you can do that because at the boundary you'd have to be still. If I'm moving here at the boundary, I'd have an incontinuity.
You have discontinuity,
Yeah.
like seawater, and small air is flowing on the seawater.
But we
If it
said
is-
that can't happen because of the viscous equation. So what gives? Because
What can happen?
if
The wind flows over the water surface. If the wind flows with very small speed, it will not disturb the water that much. It will still remain in the linear regime. Because of viscosity, you will see the velocity is going down, but it's not unstable. If the wind speed increases very fast, then you see it is taking water along with that. Then this instability takes place, and we will derive the condition what wind speeds or what density ratios cause the fluids to become unstable. So these are the regimes where we understand the instability. Third is, which is not exactly instability, which is gravity waves, not gravitational waves. Gravitational waves are different. Gravity waves are different. We always take the example, you put a small pebble on the pond and it produces waves. So even if you have this kind of configuration, the denser is at the bottom, the lighter like air is at the top, and there is a small perturbation which you cause by putting the pebble. These perturbations propagate on the surface, but it does not make the system unstable, but it's temporary instabilities. So these are the two main instabilities we will study. So now let's have a little bit of picture of turbulence, how it grows, and what we can do mathematically, and where we are stuck. We do the same thing, but this time the conditions are different. Previously what we assumed, the fluid is not moving at all. Now the fluid is moving with speed v0, and then you add a perturbation v prime. Assume the fluid is incompressible. because the fluid is incompressible, we don't have density perturbations anymore. Okay. And we have just molecular viscosity nu. If you perturb V, the equations in the perturbation becomes, let's call it V1. V1. So replace this, only took the conditions, the terms which had the perturbations.
This is small perturbation.
It's a small perturbation. You always start with a small perturbation. But our target is to understand what happens with the perturbations later on. Purpose is to study this, how this perturbation grows in time. Okay? The steady flow. Steady flow satisfies the Navier-Stokes equation. Steady, so this is okay. So this is the equation of the perturbation, and this is the equation of the fluid when it is steady. When you solve equation 1 for the perturbations, it depends on the condition of the system, what solution will come. But in general, the perturbation that you give is always periodic. Right? And it's understandable why we say that the perturbation should be periodic.
Because you can assemble non-periodic perturbations from like lots of sine waves if you really want. It's a very
Not because of that reason. I mean, it's not a mathematical question, it's physical question. From the physical property of the system, if you perturb it, the system resists against the perturbation. We saw in sound. This is why we take only the periodic perturbations. You perturb it, it resists, so that's why there is an oscillation. So we look at the solutions like this. Mathematically, you will get different types of solutions, but we expect perturbation periodic because system has periodic nature. It's like an oscillator, yes.
Mu is supposed to be squared in 1.
No, it's not square. Okay. So the solution that we expect is it depends on space and time. real part of this solution will be sinusoidal solution, the cost part. Here omega is the frequency of the perturbation here. It depends on system. If you take two oscillators, different oscillators, and you oscillate them, omega does not depend on how much energy you induce. Every oscillator has constant frequency. So if you give frequency, omega frequency oscillator, and you give this kind of perturbation V1, how this perturbation should grow. As the perturbation has exponential I omega t, in which condition the perturbation will grow in time.
Omega is complex.
Hmm?
Omega is complex, right?
Omega is complex, negative. If imaginary part of omega is negative, this is negative, it becomes iota squared plus e to the power some constant and plus t. This is how the perturbation will grow in time and will make the whole system turbulent.
Is there a reason that here omega is capital and there it's not, or is it the same? Or,
Omega? Omega is omega.
well, you have omega in the exponent and omega here in the V1. No. Is it R?
This is R.
Oh.
This is space. We assume that velocity depends on
So it's capital R. Okay.
it's a small r.
That's smaller.
It's a space and time.
Okay.
Let me try.
I understand. Okay.
So I said space and time. So the standard stability analysis is if you get the solution with imaginary values of omega, the complex value, the imaginary value is negative, the imaginary part is negative, then the perturbation will grow. Okay? However, there is no reason that why in a viscous flow it becomes, if you give it a certain perturbation, there is no physical reason why it suddenly starts, it starts growing. So there is no analytic solution.
But why is omega not a variable we can control? Because we are setting perturbation. So how can we discover omega if omega is given?
Omega is given. Okay? But you perturb the system, it's a physical perturbation. It's propagating in, let's say, flow in a pipe. It's propagating. You give it a perturbation. The condition is the perturbation is very small.
What's written there in the imaginary part of omega?
Imaginary part of omega is negative.
Oh, okay.
Okay? When V grows in time.
Positive, because you go to minus if you have positive imaginary part.
Yeah, you need it to be only in comparison.
What?
I mean, if the imaginary part of omega is positive, then you get an increasing solution.
Yeah.
Because you have minus I omega t here. If you
Right,
write
right,
I
right.
omega t, then it's
Oh, so it's positive. Okay. When it is positive, it's I square. When it is positive, the imaginary part is positive. It has iota square becomes plus. So you need the solution for omega to be positive. So we try to solve these problems in which condition you get omega to be positive so that the perturbations grow. So in all the conditions that I highlighted before, if there is an interface of two fluids, where the heavy fluid is above, gravity is below, or there is a velocity between two fluids, In those conditions, we will mathematically produce the situation where this condition is met, but not in simply moving fluids. Here the perturbation it decays with time. Physically, why? Because why should the perturbation grow? Okay, forget about mathematics. Physically, why should the perturbation grow?
Because it's unstable. The position it's
Perturbation grows, or perturbation has energy. It grows when it takes the energy of the system. And there should be a mechanism through which it takes the energy. And there is. The very fact that the nature has turbulent flows, it takes the energy from the system. But in principle, what we expect from the equations is that the perturbation should decay with time. However, we know it from experiments that mostly done by in the beginning by Reynolds, that if the flow, all the studies that we did before is for small Reynolds number. Small Reynolds number, the flow satisfies the equations we derive. High Reynolds number, what is Reynolds number? Reynolds number is it's nu d by theta. Okay, this is viscosity, this is velocity. So we saw this. When this number is very small, fine. When this number is higher, 10, 100, thousands, the system breaks stability. And this is experimental now. So when R becomes greater than R critical, let's say, the flow becomes turbulent. So we can take a couple of cases of turbulent flows, but from here I would like to switch to instabilities. And if we have time at the end, which I believe mostly we will not have because there are a lot of things to complete. Not a lot, but there are important topics to complete in the syllabus. So we'll take the instabilities first, where we will solve these eigenvalue problems and find where the omega is positive so that it grows in time. How many lectures are remaining? Yes.
That's a hard question to answer.
So it's 7th lecture today. I had 13 lectures total. 7th lecture today.
That's the 7th. I
7th
think
lecture.
there's one more. Let's check now.
One lecture was washed out because of holidays. So technically it is 8.
Okay.
And
Yeah, maybe 13 already accounted for.
Huh?
Yeah, if they told you it was 13, then wouldn't they have accounted for that vacation?
Oh, when is the last date of the
It seems we're 14.
Yeah, there are 14 lectures.
14 lectures,
Yeah.
including that? When is the last date of the
The
course?
1st of July.
1st of July? Yeah, long time, it's 2 months. By
Yeah.
the 1st of July, we'll have classes. I think
3rd of July.
3rd of July.
Yeah.
And the exams start from?
Exams start on the 4th of July. That's comforting.
Okay, 3rd of July is okay.
First of July is Tuesday, so
No,
that's
the
the last
exam-
lesson we'll have. 1st of
Then
July.
there should be 7, 8
So how many
lectures
weeks?
more.
1, 2, 3,
Okay, I just remembered it.
8.
8 lectures.
Unless
This is
can,
the seventh
unless there's
lecture?
This is 7th lecture?
Yeah, we have 8,
We have
9,
7
10,
more.
14. So we have 6 more lectures.
7.
7 more lectures.
Yeah.
Wonderful. We'll finish almost 10. But we have important things to do. Still, it's half, we are halfway. Okay, so we take instabilities in next lecture. Okay? We call it today. And in next lecture, we'll finish all the instabilities in the lecture itself.
Okay.
כתוב שהתקופה יכול ליצור מה שאתה רוצה. נכון, יש חדיות דווקא. לא, אז נכון זה הלימיט
This is why I'm taking. I will take this.
אתה לא יודע לקרוא במעגל שלך, אני לא יודע מה הוא מדבר.